Thanks for stopping by. Beautiful out today, isn't it? Well, as much as I like being outside and playing badminton, there's nothing wrong with a little bit of algebra. And today, we're going to find out that some of the work that we've learned about combinations, some of the work we've done with combinations, is going to help us with what's called the Binomial Theorem, which has to do with algebra. Now, some of you learned about the Binomial Theorem in grade 11, and some of you didn't, and that's okay. But even if you did learn about it, you're going to see it a different way now that we've talked about combinations. So come on, let's get to it.
So we're going to talk about Pascal's triangle to start, and then we're going to move in and we're going to show how that's related to what's called the binomial theorem, which is actually an algebraic theorem and gives us a skill with algebra. I know we haven't done a lot of algebra in this class. Let's start with Pascal's triangle. As a demonstration of Pascal's triangle, we could consider this kid's game with marble and pegs. So you drop a marble at the top of the game, it hits a peg, and it's equally likely to go right or left. Makes its way down and lands in one of the slots down here. I'm saying that this has 9 levels, calling the first level level 0, so really 10 different levels, if you will. So the question I sometimes ask is, if you were to, say, bet on where a marble is going to land, where would you put your money? Which slot? Would you put it on the one on the far left, the one on the far right, or somewhere in the middle? Or does it make a difference? Well, let's take a look at it. Obviously, the marble has the same chance of landing on the far left as it does on the far right, but what about in the middle? What we could do to answer that question is we could actually look at the number of paths there are for the marble to take, and at the end see how many of them land in each slot. And that would give us an idea as to where the marble is more likely to go. The first thing I'll tell you is there's only one way. I mean, the marble gets here, and there's one way to get there. It drops there every single time. There is one way for it to end in this spot, and there is one way for it to end in this spot. It has to go left to here, get here, and it has to go right to get there. Okay, move on to level 2 here. There is one path to this space, and there's also one path to this space. Okay, it's got to go left and then left again, or right and then right again. But there are actually 2 paths to this square here, because it could have came from up here or up here. In fact, if you think about this space right here, it's really, there are 2 ways to get to this space, because you could go left and then right, or you could go right and then left. Left, right, okay, right, left. Still going to get to space 2. Continuing on, notice there's always just one path along the edge here. There's only one way, in fact, to get all the way down here. You have to go left every single time. And there's only one way to go this way. You have to go right every single time. As soon as you don't go right, you can't end up in this space right here. Let's look at the more interesting paths in the middle. There are 3 ways to get here. Why? Because you could have came from here, or you could have came from here, and there were 2 ways to get there. Another way of looking at this 3 right here is to say you could have went left, left, right, or you could have went left, right, left. That would also get you there. And finally, you could have went right, left, left, right, left, left. There are 3 ways to get to that space right there. And we'll come back to that in just a minute. There are also 3 ways to get to this space. As I move on, I really just have to look above. There's 1 way to get here and 3 ways to get here. That means there's 4 paths to get to this spot. There are 3 ways to get here and 3 ways to get here. There are 6 paths to this spot, 4 paths to this spot. I'm going to continue filling this out, and I'm just going to be adding like that. And that will give me the total number of paths. Let me just speed this up a bit for you. And there's the rest of the total number of paths. So as you can see, the marble is 126 times more likely to end up in the middle as it is on one of the outsides. This triangle of numbers is actually called Pascal's Triangle. It's Pascal's Triangle written to 9 levels, starting at 0 and going all the way to 9. Notice you can identify the level of Pascal's Triangle, or the row, based on the second number. So level 9 always has a 9 here, level 8 has an 8, and so on, and then we call this one level 0. Now, how does these numbers have anything to do with what we've been talking about in this course? Well, let's go back to looking at the reason there were 3 paths here. The reason there were 3 paths here is because you could go left, left, right, or left, right, left, or right, left, left. In fact, this square represents all the paths of length 3 where left or right is an option and where there is only one right turn. So really, this is the number 3, choose 1. Pick where you want your right turn to be. Either the first turn is right, the second turn is right, or the third turn is right. If I move on to say a more interesting example, like let's look at 15 here. How do we get a 15 there in level 6? If we look at this, we realize that there have been 6 left and right turns when you get to level 6. So you've had 6 turns. So it's all of these represent L's and R's of length 6. Well, this one here at 15, there have been exactly 2 right turns, and the rest, pardon me, are all left turns. So one way to get to 15 there would be to go right, right, left, 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 left. Just think about that. Right, right, left, 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 left. Another way might be right, left, left, right, left, left. Think about that one. Right, okay, left, left, right, left, left. So this number 15 is actually 6, choose 2. Because you're taking these 6 different spaces and you're choosing 2 of them to be right turns and the rest are all left turns. You could also look at it as 6, choose 4. You're making 6 turns and choose 4 of them to be left. You might also look at 6, choose 4 as being this space right here, which is also 15. It doesn't really matter. What about the 20? Well, 20 is 6, choose 3. 6 left and right turns, choose 3 of them to be right turns. So maybe the first 3 are right. 1, right, 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 and the rest are left. Left, left, left. 6, choose 3. So Pascal's triangle, you might have even seen it in grade 11, but you probably didn't realize that Pascal's triangle is really a bunch of combinations. Let's just take a look at the next little screen here. And you can see those numbers could also all be written like this. Okay? 6, choose 3, 6, choose 2, 6, choose 4. So every single, like this is level 0 again, level 1, and so on. Level 9 is all the possible choosing you do. So level 5 is made up of 5, choose 0, plus 5, or 5, choose 1, 5, choose 2, all the way to 5, choose 5. And there are the numbers again down below for you, for you to check. Now, the Pascal's triangle does not stop at 9 levels. It goes forever. I've just shown you the first 9 levels corresponding to the first 10 rows of Pascal's triangle. By the way, 0, choose 0 is defined as 1, in case you're wondering. We know what every row of Pascal's triangle would look like, so we can figure out what, for example, the 12th row of Pascal's triangle would look like. It would start at 12, choose 0, and the next one would be 12, choose 1, followed by 12, choose 2, all the way to, of course, 12, choose 10, 12, choose 11, and 12, choose 12. Now, notice 0 to 12 is 13, so they're actually 13 different numbers in the 12th row of Pascal's triangle. 12, choose 0 is 1, 12, choose 1 is 12, 12, choose 2 is actually 66. You probably use your calculator for that. 12, choose 10 is also going to be 66. Choosing 2 from 12 is the same as choosing 10 from 12. This is also 12, and then, of course, 1 as well. Pascal's triangle also reveals what's called Pascal's identity. Let's look at Pascal's triangle. We'll just back up here, and let's look at 5, choose 2, 5, choose 3, and 6, choose 3. Notice that we figured those out in the marble game as well. 5, choose 2 would be right here. And 5, choose 3 would be right here. And notice that we got the 20 by adding 10 and 10. So the same thing is true here. 6, choose 3, which is 20, is equal to 10 plus 10. We can always get a number in Pascal's triangle by adding the 2 above. So basically, if we look at 5, choose 2, 5, choose 3, the number below and in between them is 6, choose 3. And we know that 5 choose 2 plus 5 choose 3 must be equal to 6 choose 3. And Pascal's identity tells us that in general that's always true. N choose R plus N choose R plus 1. So here our N was 5. So 5 and our R was 2. So 5 choose 2 plus 5 choose 3 will be equal to N plus 1 choose R plus 1. So for example, if I wanted to, I could say that 10 choose 6 plus 10 choose 7 is going to be equal to 11 choose 7. Why? Because I think about Pascal's triangle and counting paths, and that's always true. Okay, let's move on now to the binomial theorem. What in the world does Pascal's triangle have to do with algebra? We're going to find that out next. So there are a lot of interesting properties with Pascal's triangle, by the way, but the binomial theorem is really the one we want to look at. So I know we're really going to shift things up here. We're going to look at expanding again. Okay, let's look at some expanding of what are called binomials. So a binomial is an algebraic expression with two terms. So x plus y, each of these is just x plus y. So let's look what happens when you square x plus y. So remember that x plus y squared means x plus y times x plus y. And we've all seen distributive property, or what sometimes is called FOIL. So we can multiply x plus y times x plus y by doing x times x to get x squared, x times y to get xy, y times x to get another xy, and then y times y to get y squared. Or as I like to think, everything in the first set of brackets times everything in the second set of brackets. Now, if we collect the like terms here, we get x squared plus 2xy plus y squared. Let's look at x plus y cubed, which is, of course, x plus y times x plus y times x plus y. Now, if we like, we've already figured out what x plus y times x plus y is. So we could replace that and just say it's the same as x plus y times our answer from above, x squared plus 2xy plus y squared. So you start by multiplying everything in the first set of brackets by everything in the second set of brackets. So we're going to multiply everything by x first. That's going to give us x cubed plus 2x squared y plus xy squared. There I multiply everything by x. Now we multiply everything by y. So y times x squared is x squared y. I always write the x's before the y's. Plus y times 2xy is 2xy squared. And y times y is y cubed. The last step here is to collect like terms. So I can add x squared y. So I've got a 2x squared y plus an x squared y. That's going to give me plus 3x squared y. The next term I have is I have an xy squared plus a 2xy squared. That gives me 3 as well. 3xy squared. And finally, I have the y cubed. Okay, you'll notice I'm putting my coefficients in red here. It's because I want to point something out. Let's look at x plus y to the power of 4. So x plus y to the power of 4 is x plus y times x plus y times x plus y times x plus y 4 times. Or we could look at it as x plus y times x plus y cubed. Because we've already figured out what x plus y cubed is, it's going to make things a little easier. X plus y cubed was x cubed plus 3x squared y plus 3xy squared plus y cubed. Okay, this isn't fun, but don't worry. We're trying to find a pattern here, and we are going to find one soon. So I start by, I want to multiply everything in the first set of brackets by everything in the second set of brackets. So I start multiplying everything by x. That gives me x to the power of 4 plus 3x cubed y plus 3x squared y squared plus xy cubed. I then multiply everything by y. I might run out of room here. Let's see. Plus x cubed y plus 3x squared y squared. And I still have two more, and I'll write them down here. Plus 3xy cubed plus y to the power of 4. So there it is expanded, but not simplified, because there are a lot of like terms. There's only one x to the power of 4. Let's look at the x cubed y. There's an x cubed y, a 3x cubed y, and there's another x cubed y over here. Okay, so that's going to give me 4x cubed y. Actually, I'm going to write that in red too. 4x cubed y. The next term I'm going to look at is the x squared y squared. Notice there's 3 of them here and another 3 here, so that's a total of 6. X squared y squared. Okay, the next term we have are x cubed y's. So there's an x cubed y here, one of them, but there's, sorry, I want to look at xy cubed. There's 3xy cubed here, and there's 1 here, so there are actually 4 of those as well. And then we have the y to the power of 4, and there's of course only the 1 of those. Probably not too big of a surprise that we have 4x cubed y's, and we also have 4xy cubed. Do you kind of see how those are the mirror image of each other, and there should be the same number of them? Now let's look at what I call the coefficients. 1, 4, 6, 4, 1. Here we have 1, 3, 3, 1, and in the first example, 1, 2, 1. Notice that those numbers that I've drawn in red are actually from Pascal's triangle. When we expanded x plus y squared, we used these numbers here for our coefficients. We ended up with these numbers here when we did to the power of 3, x plus y to the power of 3. And we used those numbers when we did x plus y to the power of 4. So if we were to look at x plus y to the power of 5, you might think that pattern still holds, that we would have, instead of 1, 4, 6, 4, 1, let's look at the 5th level of Pascal's triangle. 1, 5, 10, 10, 5, 1. And we will get that. And notice the x's and the y's. Notice it started off with x to the power of 4, and then it went up to x cubed, sorry, down to x cubed, down to x squared, down to x until it was gone. And as the x exponents counted up, the y exponent, sorry, as the x exponents counted down, the y exponents counted up. So we might actually take a good guess about what x plus y to the power of 5 looks like. Well, first of all, we might use the 5th row of Pascal's triangle. Notice Pascal's triangle is actually pretty easy to just jot down. Like I'm just doing this by 1s on the outside and then adding the 2 entries above, just like we did at the very beginning of this lesson. And there it is right here. Here's the 5th row of Pascal's triangle. 1, 10, 10, 5, 1. So our first coefficient is going to be a 1, and it's going to be x to the power of 5. We don't normally write the 1 down, but in this case we will. Our second coefficient will be 5. And it'll be x to the power of 4 times y. Our next one will be a 10, x to the power of 3, y squared. So the x's are counting down and the y's are counting up. Another 10, but this one is x squared y cubed. After the 10, we have another 5. In this case, we're now down to x, y to the power of 4. And then our last one, of course, is y to the power of 5. And there it is. That's how you can use Pascal's triangle to expand a binomial without needing to go through all that algebra that I did before, which was quite painful. Now, you don't always have x plus y. Suppose you had a plus 2 to the power of 6. The first term is going to be a to the power of 6. So your x is now an a, and your y is now the number 2. We can complete another row of Pascal's triangle here. The 6th row, or the 6th level. Looks like that right there. So I can use the 6 from Pascal's triangle, a to the power of 5, and now I have a 2. So I'm just going to write times 2 instead of having a y. plus 15 is the next number, pardon me, in Pascal's triangle. A to the power of 4, 2 squared instead of y squared. The next number is a 20. A to the power of 3, and now 2 to the power of 3. A 15 again. And now I have a squared, 2 to the power of 4. And a 6. A times 2 to the power of 5. And finally, a 1. We don't need to write that. And 2 to the power of 6. Now this one's a little different because there was actually a number here. We can actually simplify this quite a bit. Okay, I got 2 times 6, which is 12. So 12a to the power of 5. Plus 2 squared is 4. And 4 times 15 is 60. So we actually get 60a to the power of 4. 2 cubed is 8. 8 times 20 would be 160a cubed. Okay, looking over here, I've got 2 to the power of 4 is 16. And 16 times 15 is 240. A squared. Then finally, 2 to the power of 5 is 32. 32 times 6 is 192. And 2 to the power of 6 is 64. So there's the final answer in simplified form. Why does binomial theorem work? Like, why is it that the numbers in Pascal's triangle correspond to the coefficients and the expansion? Well, you don't really need to understand that to work on these kind of problems, but I think it's certainly a good idea. You might look at x plus y to the power of 5 as x plus y times x plus y 5 times. Why is it that there's one x to the power of 5? Well, the answer is there's only one way to get an x to the power of 5. You have to multiply x times x times x times x times x. There's the x to the power of 5. And there's only one way to get a y to the power of 5. Y times y times y times y times y. Y to the power of 5. However, there are 5 ways to get x to the power of 4 times y. Because you could do x times y times y. Sorry, you could do y times x times x times x times x. That's one way. Or you could do x times y times x times x times x. That would give you x to the power of 4 and y. Or you could do x times x times x times x times y. There are 5 different ways, or 5 choose one ways to pick the y that's part of the multiplication. And as far as x cubed y squared is, there are 5 choose 2 ways to choose the 2 y's that are part of this term. It could be y times x times x times x, or it could be x times y times x times y times x. That would also give you an x cubed y squared. So you can kind of see how it's very similar to the marble game. The number of paths to this point is the same number of paths that will give you an x cubed y squared when you expand. I know that's a little bit complicated. Keep in mind that this number 10 here is in fact 5 choose 2. 5 choose 0, 5 choose 1, 5 choose 2. There is another way to talk about binomial theorem, and that is using this formula. And if the formula confuses you, don't worry too much about it. You don't technically have to use it. Let's take a look at the second formula that we have that doesn't use the summation notation. It's basically telling you how to use binomial theorem with a formula. So if I had an example, let's say x plus y to the power of 10 even, I could use this formula. Here my n is equal to 10, and I've kept x and y as x plus y, but they don't have to be x plus y. They could be a or b, they could be numbers too. So this is going to be 10 choose 0 times x to the power of 10 plus 10 choose 1. X to the power of n minus 1 is now x to the power of 9, and now we have a y. Plus the next one will be 10 choose 2. X to the power of 8, y squared. 10 choose 3, x to the power of 7, y cubed, all the way until I get to n choose n, which in this case is 10 choose 10 times y to the power of 10. And then, I don't know, how do you get the coefficients? Well, you could either use your calculator. In this case, maybe using your calculator is the easiest. You could use Pascal's triangle if you like. So you don't have to use the formula. You could go all the way to level 10 in Pascal's triangle. this formula, the first formula, just takes that idea and changes it into summation notation. So you don't need the dot, dot, dot anymore. So if I did x plus y to the power of 10, I could then say that's the same as the sum of k equals 0 to 10 of 10 choose k x to the power of 10 minus k times y to the power of k. So I plug in 10, or I start by plugging in k equals 0, and I get this first term down here. Then I plug in k equals 1, and I get this next term down here. To k equals 2, I get the third term, and so on. Let's try another example. 2x plus 1 to the power of 5. So again, you have a choice. You can either use the formula. You can write Pascal's triangle out. It is not that difficult to do. In either case, you want the fifth row, which is the one that starts with a 5. So how you get those numbers is up to you. You can just do what I just did right here as I was talking, or you could say 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. Okay, the first coefficient is 1, and now we have, instead of x to the power of 5, it's 2x to the power of 5. Make sure you include the brackets. You do need those. The next term has the 5 from Pascal's triangle times 2x to the power of 4 times 1 to the power of 1. Moving on, I have a 10, 2x cubed, 1 squared. Another 10, 2x squared, and now it's 1 to the power of 3. A 5 times 2x to the power of 1, or just 2x. 1 to the power of 4. And then finally, my last one, 1 to the power of 5. Notice Pascal's triangle has exactly the right number of coefficients that we need if we're going to take 2x with the exponent 5 and count it all the way down until it's gone. The last step is to simplify. Be careful here. 2x to the power of 5 is 2x times 2x times 2x 5 times, or 2 to the power of 5, x to the power of 5. It's 32x to the power of 5. Then my next one, 2x to the power of 4, that's 16 x to the power of 4, but when you times 16 by 5, you're going to get 80. 2x cubed is 8, and then 1 to the power of 1, 1 to the power of 2. Those are all just 1, so they don't actually change anything, which is kind of nice. You get 80x cubed. 2x squared is 4. That's going to be 40. 40x squared times 1. This is just going to be 10x, and then 1 to the power of 5 is just 1. And there you have it. How about 3x minus 2 to the power of 4? So we've already got the fourth row of Pascal's triangle. There it is right there. Those are going to be the initial coefficients. Those are the coefficients, like the number out front before you do the multiplication, before you simplify. So 3x minus 2 to the power of 4, I'm going to use those numbers, 1, 4, 6, 4, 1. Okay, or 4 choose 0 all the way to 4 choose 4. And my first one will be 3x all to the power of 4. Plus, okay, 4 from Pascal's triangle, 3x cubed times negative 2 to the power of 1, or just negative 2, plus 6, 3x squared, careful with the brackets, times negative 2 squared. Then I have a 4, and I'm at 3x to the power of 1, or just 3x, times negative 2 cubed, and then finally my last term is negative 2 to the power of 4. Be careful, again, simplifying here. 3x to the power of 4 is 3 to the power of 4 times x to the power of 4. That's 81 x to the power of 4. Now, what happens, though, with my negative 2? This next term is going to be negative. So 3 cubed is 27. Okay, 27 times 4, which is 108, but then times that by negative 2, and you're going to get minus 216 x cubed. Notice that in this one here, I'm going to have a positive 4, because negative 2 times negative 2 is positive 4. These terms are going to alternate between positives and negatives. So 3 squared is 9. 9 times 6 is 54. Times that by 4, and you get 216. Happens to be 216 again. 216x squared. Okay, there's the x squared there. Okay, the next one's going to be negative. Negative 2 to the power of 3 is negative 8. So if I multiply negative 8 times 3 times 4, I will get 96. So in this case, negative 96x. And then negative 2 to the power of 4, since it's an even exponent, it's going to be positive. It's just positive 16. There it is right there. Okay, so that's binomial theorem. Really all I want you to take away from this lesson is the ability to use binomial theorem for simple binomials like this, to understand that Pascal's triangle gives us the coefficients in the expansion and sort of have an understanding of why. And also I'd like you to understand that this idea that Pascal's triangle is made up of combinations like this. Okay, good luck with the assigned problems, and bye for now.